Okay, you guys, here I go. Suppose I got a function f whose output could be expressed in the following funky fashion. I know it looks awkward, but we'll clarify this in the next hour and a half. Suppose the output of my function can be expressed as a sum, as n ranges from here to here, of some coefficient c sub I, n, times x minus a to the n power. If the output of my function can be expressed as such, I might refer to this thing right here above my brace. It's called a power series representation. For the output of my function f in terms of x. And it becomes tremendously useful to be able to express functions in terms of power series for lots and lots of reasons. Number one, jeepers, you guys, these are power terms. So it's easy to, gosh, what's that math theory thing called? It's easy to differentiate and to differentiate. In addition, it's going to be easy for me to algorithmically make computations for the output of my function because all expressed in terms of simple multiplication and addition, particularly when it comes to transcendental functions. So I do think it's a big deal. But if I can express a function in power series form, it kind of suggests to you guys, I got to get a handle on what C sub n look like. I need to know what the C sub n's look like. And only because you guys might have questions on this, do you think I can bend your necks a little bit? Can I go over there so I can keep it on board all day today? Okay. So you guys, you're gonna have to sit there and watch me play for a few minutes. Everything I'm gonna say for the next few days depends on just this. So I'm gonna make a supposition. Suppose the output of my function can be expressed as a power series. By the way, it means that first term is going to be generated when I plug 0 for n. It's just simply this. My second term is c sub 1 times x minus a. My third term is c sub 2 times x minus a twice. My fourth term is c sub 3 times x minus a thrice. My fourth term, I'm sorry you guys, I'm not trying to put you to sleep. It's just too important. I want to put a lot of terms in there. Now, if I were to come in and differentiate, I think it tells me f prime of x is this. I want you guys to just kick back, relax, and just double check my work, double check my math 30 skills. I think my next derivative is going to be this. I think my third derivative is going to be this. And you guys, if I came in with each and every one of these mathematical statements, and I don't know, if I had my function f at a very interesting value of x, how about f of a, or f prime of a? Or maybe f double prime of a, or maybe even f triple prime of a, you check out how nice my arithmetic is. When I plug a and for x up here, everything drops out. Except the first column. That's so big, I'm going to circle it. I think if I value f prime at a, I see that prime is equal to c1. Oh, that's so important, I'll circle it. I think when I take my second derivative function, evaluate when x is equal to a, oh, I get some different coefficients. I guess that looks like a 2 times c sub 2. I'll circle it. Down below, plugging a in for x, I guess everything drops out except the first term. That's just 3 times 2 times c sub 3. I'll circle it. You guys, because of what you know about the differentiation process, because you're such experts at differentiating using the powerful differentiation, tell me what you think you can possibly say about the nth derivative for f at x equals a.
It's n factorial
Times c sub n. Can we say it differently? can we just say that C sub n is equal to the nth derivative for f at x equals a over n factorial? And so I maintain if a function f has a power series representation like that over there, I got a darn good handle on what those coefficients, the C sub n's really look like. They're nothing more than the nth derivative for f at x equals a over n factorial. In English, I might say that this is a power series centered about x equals a. And I think this being the case, I've got a handle on what the C sub n's look like. There's nothing more than this. And I think that's pretty darn slick stuff. Matter of fact, I think I've got some power. You guys, hear me for a minute. Consider this function f. What's this derivative? Oh, you've got this.
Negative sign.
Say it again. Negative cosine x.
Negative sin x.
Get the idea. So I think if I had a power series representation for the cosine function, I think it's going to look like this. Sum as n ranges from 0 on up of my C sub n times x minus a, which in this case is 0, raised to the power. I want to find a power series centered about x equals 0. I think it's just simply this. Let's see if we can get a handle on what these things really look like. I guess it would be the nth derivative for f, evaluated at x equals a, which in this case is 0, all over n factorial times x to the n. Let's do an expand out. I think the 0th derivative, that's the original function, evaluated 0 is equal to
1.
Oh, I'm sorry, I meant to say over 1 factorial times x to the 0 power. It's just 1, isn't it? Now I'll slow down. If n is equal to 1, I've got the first derivative function evaluated 0, which is 0. Can I not write the rest? Drops out. When n is equal to 2, I got the second derivative function evaluated 0, but that's just a negative 1 over 2 factorial times x to the 7th power. Plus, well now when n is equal to 3, I don't have to worry about it. The third derivative evaluated x equals 0 is going to be equal to 0. But now when n is equal to 4, my fourth derivative function evaluated 0 is positive 1. So I guess I get a plus 1 over the 4 factorial times x to the 4th power. Did you guys see the pattern developing? I think my nth term is simply going to be a 1 over the test this tomorrow, right? Pattern.
2
2n
factorial
times x to the
and 2n.
2n power. And so I think in the end we can express the cosine function as this power series as n ranges from 0 on up is just simply my 1 over 2n factorial times x is 2n power. Are you happy? I'm not. There's something wrong with this. What is it? Yeah, I think it's alternating. As an alternating series, I think I need to incorporate them. So I think this numerator could be interpreted as negative 1 raised to some power. And I'm being honest, I don't remember what power. Well, let's just put it in. If n is equal to 0, it should be positive. If n is equal to 1, it should be negative. So we shouldn't do this. You don't believe me, you can test me. So I think I have this. So you guys help me with this. With this power series. If I only got the very first term, what does it look like graphically speaking? What does it look like graphically speaking?
It's a dot.
It's more than that, so it's really many dots.
I thought we were just grabbing the first term.
Yeah, if you graph the first term, what would you get?
1.
A horizontal line.
Oh.
So everybody, I gotta slow down. I just walked into this classroom. I don't know what's going on with this computer. Let me turn my calculator on. Ooh, type in the cosine of x. And let me type in the first term, y equals 1. And let's see what happens. Well, maybe not see what happens. Hang on to my limit real quick. I don't know what it looks like. How about an x min of, how about negative 2? Positive. And maybe a y min of negative 5, positive 5. And let's graph. So you guys, the first curve is nothing more than my cosine function graph. And I think what you see coming in next is nothing more than the horizontal tangent line. It is tangent to the graph of f at x equals 0. Or you could say what I've just graphed is a linear approximation for the cosine function about x equals 0. I admit it's a lousy approximation, but locally speaking, it does approximate the y values in the curve if I just choose that horizontal line. I just think I can do better. Because now what I'm going to do is type in the first two terms, which, by the way, is a quadratic function. It's a parabola that will be the best fitting parabola to my graph about x equals 0. I still don't like my range. If you guys don't mind, I'm going to change it real quick. And now when I go into my equation editor, I will add to this by minus. You guys, what is that fraction? Is it 1 over 2 factorial? Times my x to the second power. And now check out what happens. There's my cosine graph. And there is the first two terms of my power series doing a much better job than before at approximating the cosine function's graph about x equals 0. That is really slick stuff. How can I do better? How can I get a better approximation? More terms. More terms. Let me add the next term in. And I think of adding the next term in over there. Oh, my equation editor. Diving down. Let's add in the 1 divided by, you guys, do you already grab your factorial function? If you go into, actually, I don't remember actually, math. Go into probability. Yeah, there it is. It's item number 4. Not that I really need it, but in case you guys have bigger numbers, you want to evaluate. And I'm going to multiply by x. Raise the power of 4. And let's see what happens. Yet again, there's my standard cosine function. And look at how nice that is. That fourth degree polynomial function, I think, visually anyways, is fitting my cosine curve pretty darn well, locally speaking, about x equals 0. It's just that from now on, you guys, I get to consider that the infinite collection of terms is exactly equal to the output of that cosine function. That's significant. Are you there?
So,
Yes.
can you clarify something
Yes.
for me? Just when you've got f to the end, which is, that's your derivatives, right? Or that's a derivative, right?
Yeah, so in English,
So-
I would never say f to the n. I would have said the nth word.
Or the nth derivative, yeah. So how do you get the numerators there? Can you just show the steps in between, the series to, yeah,
From here to
that
here.
one to that one, yeah.
Actually, I did it term by term.
Okay.
When it came to the first one, I just simply said, let me get some more room in here. I simply said for the first term, I've got the 0th derivative for f of at 0 over 0 factorial times x to the 0 power. Plus the next term, which is the first derivative for f, divided a over n factorial, which in this case is 1, times x to the first power. So plus the second.
Okay, yeah, I see what you're doing. All right.
So it's just s sub 0, s sub 1, s sub 2.
Yeah, where's the 0 coming from the function?
Oh, in English, I asked for a power series expansion about a equals 0. I think I said x equals 0 means the same thing.
So that's the position of the graph.
Yeah, and if I dove in here and found a power series expansion about x equals pi halves, that just simply means all my functions are, locally speaking, around here, going to be very close to my cosine wave, which I could just as easily done.
So, how would you handle the indexing?
How would I?
Do the indexing for this?
Now, the index variable is simply incrementing by 1 unit. So n starts at 0 and goes up 1 for every single
So
time.
it's S then?
These are f's. These are f's. That's my function n.
No.
It's 0.
Oh,
zero.
right, okay.
Yeah, I'm just going back to what these coefficients, my c-spins look like. And they're in terms of an order derivative for us.
So it would be C sub 0, C sub 1.
Yes, yes,
Okay.
exactly. I think what you're looking at in front here is c sub 0 times x is 0
Okay.
plus c1 times x to the first, et cetera, et cetera, et cetera. I agree. Yes, sir.
Can you explain the alternating part again? Because with the derivatives, we go positive, negative, negative, positive, positive.
Ah, but you know what? I think when it came to valuing these beasts when x is equal to 0, every other one dropped out. Those involving signs dropped out because sine of 0 is 0. And now you can clearly see I really do consistently alternate from positive to negative. Come on, you guys attack me. This is too big of a deal.
So this is just for evaluating cosine at 0, right?
Well, this is for generating a power
the,
series
the,
of cosine.
the last two lines right here. It's just cosine valued at 0.
This is a cosine value at any value of x.
No.
But it's a power series centered about x equals 0.
So what? So if it was centered about something else, then it would be pi or whatever. Like-
Yeah, you'd have x minus a here, x minus a here, x minus a here, and the evaluation derivatives would be different because what you plug in for x is a, which is no longer 0. And I'll mess that up today, I promise. I'll have different values of a other than 0.
Okay, so the 0 just applies to the specific example?
Yeah, I was looking for a power series centered about x equals 0, so
So-
you can see my pretty picture, my curves start hugging. My curve.
Okay. So, in terms of the definition of the power series for cosine, it's really x minus a? Power series definition?
All right. You can say, you can write a
I just
power
don't want to be
series.
confused when reading this.
You can write a power series for cosine of x about any value of x. In other words, a can be anything you want. Now, typically for a sine and cosine function, we talk about a power series centered around x equals 0, just because the coefficients make it look nice. As a matter of fact, you guys, can I change my wording? When I have a power series like this for a function, centered about x equals 0, I sometimes subclassify them as a Maclaurin
Yes.
series.
So this is the Maclaurin series for cosine of x.
And if I've got a power series centered about a value of x other than 0, I may call it a Taylor
Okay.
series. Now I have to confess, though, to come back to this random, when I think of the cosine function and think of a power series representation for it, I typically do have this specific one centered about x equals 0. And if you...
0
yes.
being your a value?
0 being mine.
The a value?
Yes, so in other words, a is equal to 0.
Okay.
And if you guys don't mind me cheating, your author does not do this. He derives a power series expansion for the sine function instead, but he's already done that for you. So I'll leave that for you to read. However, it is the case, because we're taking a break, it is the case, oh no, I'm putting myself on a spot, I gotta look for this. On page 620, he gives you a power series representation for the sine of x as well, many others, but the other ones I want to derive in class. I'm going to skip the sine function because he does a sine function in the book. Doesn't do cosine, so I wanted to come to class and derive cosine's power series representation, and you can look and see if he's done the sine of x's power series representation exactly the same way I did. It just looks a little bit different, and again, on page 620, you're going to see a table of power series representations with which you need to be familiar.
So what's the significance of this?
Yeah, well, when you add up all those values.
Hugely, hugely. Yikes, what a loaded question.
Yeah, exactly.
You know, several semesters ago, I was in my office, a student came in, and he said, you know, I'm a graduate student for computer science over at UC Davis, and I don't know if you remember me, but I took you from Math 31. I was kind of hoping you can help me. I got really stuck on writing a program. My professor has told me I've got to compute the sine at various different angles, and I have no idea how to program a computer to take the sine of 1 radian.
That's how calculators do it.
Yeah.
But because this is all expressed in terms of addition and multiplication, piece of cake to get the cosine or sine in the other case of whatever that particular input is, because we're expressing in terms of the power
This
series.
is what your calculator does.
It's exactly what it does. What's really cool about this one, because it's alternating, I've got complete control over the axiom of approximation. If I only want to grab the first n terms, I think the first unused term in absolute values, that's n plus first term, in absolute values is an upper bound for the error in my use of the first n terms for the exact value of the original function evaluated at whatever value of x we have. Pretty cool stuff, I think. And Bradley, there's so much more. I'll stop talking. But here's so much more.
So this is how you can find like cosine of some weird number, right? Like,
Yes, but,
Okay.
but even bigger than that.
Yeah.
Aren't these a piece of cake to differentiate and to differentiate?
yes.
That makes life really easy. So how the heck can we approximate pi really, really well? You just got to give me another 20 minutes.
Okay.
We will. Just 20 minutes.